Okay, hello everybody. Welcome back to lecture 11 of PSTAT100. Thank you again for putting up with my remote lectures. This will be our last remote lecture as I will be returning to Santa Barbara on Tuesday. I'm currently in Utah in my sister's house, um, and my wife is asleep in the other room. So I apologize if I'm speaking a little bit quieter than normal, but I hope that the audio is picked up fine and you can hear me. If not, I'll obviously have to re-record this at some point. Um, as I mentioned, this will be our last remote lecture. It is going to be introducing multiple linear regression. It's following the same format as last week. This lecture is going to be slightly more theoretical, with our focus in class in person on Thursday going to be in implementing multiple linear regression in Python, and also looking at the different kinds of regression that we can also add to increase the complexity of our model. Things like polynomial regression, and then also considering some methods for determining which model to use and model selection methods. I'm getting ahead of myself. Today we're just going to be introducing multiple linear regression, which is the linear regression. Instead of having one predictor, we have multiple predictors. And so to kind of give an outline of what the plan is for this lecture, we're going to introduce multiple linear regression. We're going to introduce the matrix notation for the model, where there is going to be a significant portion of linear algebra in this course, or sorry, in this lecture. There's not going to be a requirement to learn and understand each step. If it's your first time using linear algebra, to this extent, it can be quite confusing. However, it is a very helpful tool for allowing us to derive these closed form expressions, which is what we so appreciate about linear regression, is this ability to have a type of modeling where we can have closed form expressions for parameter estimates that we can compute immediately without having to do some kind of parameter optimization algorithm, which is computationally intensive. So we're going to derive the OLS estimator for MLR. We're going to show the equivalence of this multivariate case to the simple linear regression before we kind of go through the derivation of the same properties that we covered last week, things like unbiasedness, before this best linear unbiased estimator, and having a look at the variance covariance matrix for the parameter matrix, which is this beta hat that we have yet to describe, but it will make sense once we've gone through the lecture. We'll then discuss some statistical tests that we can perform once we know the sampling distributions of these parameters. And then we'll kind of finish the lecture by setting up considering model selection in future lectures, and talking about some of the model fit parameters, model comparison parameters that we will be using in future lectures to compare and select optimal models. So I've just noticed these the required libraries here is quite long because I think I copied and pasted this first slide from the following lecture, which uses these packages. So don't worry, you won't be using all of these packages in this library, but if you do replicate the code yourself, in future when I post this lecture slides, I'll update the required libraries only to have the libraries that you need. All of the sklearn functions that we've imported in the bottom sort of 3 lines, I'm pretty sure are going to just be applied for the next lecture. So anywho, to begin, I'll have a quick sip of water because my throat's been having a hard time since flying back from Hawaii 2 days ago, and then flying out to Utah today, sorry. Oh no, sorry, 1 day ago I flew back from Hawaii and then I flew out to Utah today. Hence my lack of time to prepare this material. Anyway, multiple linear regression. So let's kind of start at the beginning and have a very quick review of what we've covered so far. So we're in our data science course, we've looked at our exploration, and we've now moved on to the analysis part of the data science lifecycle, and that involves fitting models. And so we started off by considering statistical models, which are models where we have some assumed underlying structure. Specifically, we in this case are assuming this underlying mathematical structure is linear. That is, we have some response variable that we care about, and we assume that it can be described as some linear combination of predictors plus some kind of Gaussian noise. So far, we've looked at simple linear regression, which is we're considering a single predictor. However, most real phenomena are driven by multiple factors simultaneously. And it is not too difficult to think about examples of this case, because it is very, very rare that you'll have some single factor relationship in kind of modern data sets. So whether it's financial data, like prices of companies, whether it's business data and sales, there's many, many different factors that influence the response variable that we care about. And so the point of having multivariate linear regression is that in this, given the assumption that we're assuming the underlying relationships are linear, we still want to incorporate, we still wish to capture these multivariate relationships and to essentially capture as much information as possible without airing, without waltzing into the territory of overfitting, which is something we'll talk about later. So the point is the main drawback of missing these predictors is that it leads the simple linear regression slope to absorb the effect of the missing variables that are correlated with X. So the idea is that you, and this is known as omitted variable bias. So the idea is that by omitting certain variables, you are influencing the slope that is fitted in simple linear regression, and that slope may be being driven by different predictors that you don't have included. And you're essentially introducing a type of bias into your final model. So as a very quick example, remember from lecture 10 last week, we had this very simple regression of penguins, body mass versus flipper length, and we noted there was this sort of vertical / systematic banding, because we know that there is this underlying grouping in the penguins into the different islands. And this was a strong hint that this species variable had a significant impact on this linear relationship, i.e., it was potentially a different linear relationship between each species, and in this case, species was acting as a submissive variable. So we were introducing bias but not considering it. Adding this species can reduce this bias. It can increase the proportion of variance that we have explained, and it can also improve our prediction accuracy because you're giving some specific information and being able to tweak your model to be more, so you have more accurately represent each species. So multiple linear regression. Let me just make my head smaller. I realize I'm lifting too big. So in multiple linear regression, I'm sure a lot of you have seen it before. We essentially have, for some response, Y and P predictors. I apologize for the gratuitous use of indexing. It's a drawback of this multivariate cases that we introduce lots of index notations, but we essentially have P predictors, X, which we denote X1 to XP. The multiple linear regression model is defined as the response, where now we have to be careful because we are introducing the observation index I. So in this case, the beta indexing is for the different predictors. Each predictor has both a predictor index, which is given by 1, 2, up to P, and then I throughout all of the different model terms. So Y, X, and epsilon denote the observation, i.e. the individual it corresponds to, for which we have n of them. And so we write the response Y as this linear combination of the predictors, where we, and this is something we'll talk on the next slide, under the Gauss-Markov assumptions, we're assuming that the error terms, these noise terms, these epsilons are all IID normal with some variance, sigma squared. So you can see exactly the same form as our simple linear regression, but now we have to have slightly more complex indexing, and we have introduced P-1 more predictors into our model. So there are P+1 parameters. So we have the intercept, beta naught, or sorry, I should say P+2, because typically you're also estimating sigma squared. But we have beta naught, which is the intercept because it has no corresponding predictor. And then the remaining are slopes, beta 1 to beta p. And we have n observations. So I've just done a kind of quick summary of, for each I, what are the what measurements do we have for each observation I? We have the response Y and all of the p predictors. Obviously, the simple linear regression case pops up once if we set p equals 1. Everything above beta 1 disappears, and so it collapses to the model that we've seen already. And obviously, because now we have significantly more parameters, we need more data to fit the model. We technically need a minimum of p plus 2. Excuse me, I had a sugar cookie from one of the soda shops here in Utah, and just look how much icing on it. It bottomed me out. The huge mountain of icing on this cookie. Because they are obsessed with sugar here, and it's upset my stomach somewhat. But in general, because the model is more complex, we need more kind of larger data sets to fit them. So borrowing this helpful table from some lecture notes I found online, which I just realized I haven't added to the references, but I will do. We have, oh my God, that cat scared the crap. Sorry, scared the bejeebers out of me. My sister's cat is just jumped into the office. It's called Bing, I think. So in this case, we've defined our response variable as sales. We've denoted sales as y, and we have these p equals 3 predictors, which we denote x1, x2, and x3 in TV, radio, newspaper. And then for them, we have n observations. So just a quick visualization of how you can think about these kind of defined terms in terms of a table. You have your column of interest as y, and everything else, all the other columns are the different x's. So just discussing intuitively what the difference between these two models are. In simple linear regression, we obviously have the single slope parameter, and that captures this total marginal relationship between x and y. In multiple linear regression, each slope is a partial slope. So the idea is that beta j corresponding to predictor j is the expected change in y for 1 unit increase in xj. So the slope of xj, slope of y in terms of xj, if given that we keep all the other predictors constant. So given that we fix the values of all the other x's, then the beta j describes the change of y in for every 1 unit increase in x j. So I've discussed this before, just this idea of how in simple linear regression, we just had beta 1, which was this response of body mass and corresponding to flipper length. However, in multiple linear regression, we would introduce beta hat, which in this case I've described as flipper, but this would have multiple betas in it. It would have beta 1 and beta 2, beta 1 corresponding to flipper length and beta 2 corresponding to species. And we'd be able to have two partial slopes. And it's important to note that these partial slopes can differ substantially, even in sign from the SLR slopes. I mean, intuitively, that should make quite a lot of sense, because if we have different linear relationships between flipper length and body mass for each species of penguin, then these different slopes are describing that relationship for each species. And so there's no I guess in this case you'd expect them all to be positive, but there's no guarantee that the relationship has to be consistent across different species. And so you can expect the slopes to be very different from each other. Okay, so kind of getting onto the more technical mathematics of this part of the course. And this is something I will definitely cover in person on Thursday. But we express the multiple linear regression model in matrix form by defining these 4 matrix objects. So the design matrix X has p plus 1 columns and n rows. Each of the rows is for a different observation. For n observations in total, the column of ones is included as to correspond to the intercept. So if you can imagine, we will then be multiplying by this matrix beta, and so beta 0 will be multiplied by all of the ones, and so for all of the different observations, beta 0 won't have any corresponding x. And then obviously we have x11, x12, all the way up to x1p. So this is all of the different predictors for observation 1, all of the different predictors for observation 2, etc., down to n. Beta is this column vector of all the different parameters. So it has the intercept and it has all the slopes down to p. So this is a p+1 column vector. Y is the response observations for each of the n observations. So this is an n-length column vector. And then epsilon is the column vector of all of the different the noise observed for each of the n observations. Given these matrices, we can then write our model as y equals x beta plus epsilon. I've tried to keep my matrix notation, anything that's a matrix or a vector, in bold font to keep them distinguished from any of the individual responses. However, I apologize if I missed it. I tried my best. And here I've kind of jumped the gun a little bit, but we can write, because this is a vector of essentially Gauss, well, it's a vector of Gaussian random variables, and more specifically, independent identically distributed Gaussian random variables with mean 0. Hence, the vector mean is also a 0 vector, and then all of them have the same variance and 0 covariance because they're all independent. And so we have the covariance matrix here, which you can think of, this IN represents the n by n unit matrix, which is ones on the diagonal and zeros everywhere else. And so in this case, we're going to have a diagonal of all the variances equal to sigma squared, and everything else is 0 because there's no covariances. So I'm just making a note here about what I just mentioned. There's x as p+1 columns with the intercept. And the main advantage of this matrix formalization is its compactness, and it allows us to very easily derive OLS estimators using linear algebra. So before we go on to considering OLS estimation, let's have a look at the Gauss-Markov assumptions. So as I just discussed, the assumption follows through, and these will all appear very similar to the ones we discussed for the simple case. This linearity, i.e. because we are considering a vector of mean 0 Gaussian random variables, the expectation of the vector is this 0 vector. The variance, as I just discussed, is sigma squared throughout, and this is all to do with independence. So the reason this variance holds like this is because of independence. From normality, I mean, I've stated all of this on the last slide, but essentially these two properties combined plus the assumption of normality give this statement. And importantly, we also assume full rank. So we assume that all of the columns are linearly independent, and so you can't find some form of the matrix X with a lower rank than p+1. You can't simplify it down. This is something that will be familiar for people who've studied linear algebra. It's important for some of the operations we apply, but it's not super important for understanding linear regression in general. So don't worry too much about that last point if it's not super familiar for you. However, the key takeaway is that y, the response vector, is normally distributed with this mean vector given by x beta and then a variance vector given by sigma squared in. And this should hopefully be clear where this follows through from our discussion about the same or the kind of analogous result from simple linear regression, whereby we essentially have the location being given specifically by the linear relationship, and then the variance given only by the variance of the noise. Because if we go back to our model statement, we can see that if we're taking the expectation of y, the expectation of the noise is 0, and so we're left with just the expectation of xb, and this is why the mean location is given by xb. But then if we take the variance of y, this term, or sorry, when we take the expectation, this isn't random, so this doesn't have an expectation, and then this becomes 0 in expectation, so this becomes the mean location. And if we take the variance, again, this doesn't have any randomness, and so this is where all of the variance comes from, but in this case, the variance is equal to sigma squared in. So I won't spend too long on this because I'm already aware that I'm at 20 minutes, which is way longer than I expected to take. But this is just a quick example in Python of doing the same thing that we did last week, where we constructed a simple linear relationship from not with data. So this is kind of working in reverse to how we usually work in data analysis, or sorry, in data science. Excuse me. In data science, and when we are modeling with data, we have some data set. We assume the mathematical structure and we fit the parameters. In this case, I am starting with assuming the structure and defining the parameters and just feeding in completely generated noise. And then that's getting fed through this model equation to essentially reconstruct what would be a data set that we would model with it, if that makes sense. So it's essentially producing a synthetic data set that follows this multiple linear regression relationship. And I won't go into the details about this, but I've added little comments through this to hopefully, if you want to work through it yourself, but you can see here we start by setting the seed and we define all the parameters here. So we define that we want 150 observations, we want 3 predictors, we specify what the intercept is, and we specify the slopes corresponding to all of the different the partial slopes for all of the different predictors. And then we specify the noise level is 2. These have just been arbitrarily chosen. There's nothing to do with any data. There's just some numbers I plugged in to see what the results are. I then defined this design matrix and response vector. So you can see here that this is just exactly generating an n by p standard normal matrix. So all of the observations are completely uncorrelated, completely independent of each other and standard normal. I then feeding, sorry, I'm stacking this n by p normal vector with a column vector of ones. So this is producing the x with the first column is ones and all the remaining columns are these x's. These don't have any relationship yet, but then I'm imparting into them this relationship for the model that I've just constructed. So you can see here that I have this x times by beta essentially here with the matrix multiplication using the ampersand symbol in Python. Which is I think slightly different to R. Just to specify, this is essentially a shorthand version of concatenate. It's actually something I only recently learned, but this is essentially doing the same thing as NPy concat. So it's just sandwiching together the beta not true and the betas and the remaining betas, and then adding the noise with the sigma that we specified. Okay. And that's all it's doing. So this is just a quick visualization of the design matrix. You can see that these are for different observations. This is for the intercept, it's all the same. And then x1, x2, x3 have slightly different values. It's not very exciting. I kind of was thinking about removing it, but since it was in, I thought I'd include it. And you can start to kind of have an explore of this relationship that we've imparted into things. So you can see here that I've just plotted y against x1, doing a bit of flexing of using our different formatting options. But you can see that y against x1 has a slight linear relationship, but there's also this multivariate relationship that we've imparted in terms of, and we've tried to visualize it by coloring in terms of the parameter x2 and sizing the points in terms of x3. Whether or not there's a clear relationship between those variables and visual in here, it's very difficult to see. I also produced this correlation matrix to have a look. This again it's not for data. We've generated this, so this is merely to observe what we've created, and you can see that there is a strong negative correlation here. Sorry, I shouldn't say strong, like at least noticeable, but not hugely significant. And there's also a reasonably strong kind of getting on towards sort of significant positive linear relationship between y and x1. This you can see is kind of corresponding to the parameters we created, right? You can, if you remember from here, sorry, we had our slope for x1 be the strongest and positive, and then our slope for x2 be negative and the next strongest, and then a positive slope for x3 being the weakest. You can kind of see that carrying through in this matrix, where x1 is the strongest and positive, and then the next strongest and negative, and then the weakest and positive. And this kind of weakness, I guess, which is maybe evidence it was a bad example, but I digress, is shown from this pair plot that I just produced. Sorry, I believe the figure caption has been clipped off, but essentially it's just saying that you can see the strongest evidence of a linear relationship between y and x1. However, y and x2 and y and x3, even though the correlation may have seemed, worth noting, you can see that it seems it's very weak. But you can at least see the positive direction coming through x1, the negative direction coming in x2, and you can see this information we've imparted into the data. I should say, well, the synthetic data. Okay. I would ask if there's any questions, but I'm in a remote lecture, so hopefully it's going okay. Please come and see me in my office hours if you have any questions. OLS estimation in MLR. So it's worth stressing that I included this section just to show both the derivation procedure for these parameter estimates to highlight to everybody that they have closed form expressions. This isn't a magic box algorithm fitting function that's happening in Python. This is just doing a computation using linear algebra. The only thing it does numerically in Python typically is invert matrices, and that is actually a thing that's quite interesting to talk about in terms of machine learning, is that can quickly become actually the main bottleneck of these methods, is that we can analytically compute things up to inverting matrices, but once you're considering incredibly large feature spaces, which you tend to do with modern machine learning algorithms, trying to invert very, very high dimensional matrices becomes incredibly time consuming computationally, and that tends to be the main bottleneck. I've mentioned this before, I think, in the first few lectures, but I digress. Let's have a look at OLS estimation in matrix form. So I'll move myself out of the way again. The OLS criterion in matrix form is, oh, let me just double check I'm recording. I am recording, cool. So the OLS criterion in matrix form, essentially we're estimating the parameters. So again, I always feel like it's worth reminding people what we're doing because it can get easily lost in the source. What we're doing is we've assumed this multivariate linear mathematical structure is describing the relationships in this data. This is parameterized by these collections of betas. So here this beta is in bold, so it's representing beta naught up to beta p. And we're looking to estimate them. We're looking to find the parameters that best suits the data that we're providing to it. And we do so with ordinary least squares. So as a reminder from last week, the OLS estimator is the value of the parameter vector. So this, I say the value of beta, but this is the p+1 value in the vector that minimizes the residual sum of squares. Okay, so this is the exact same expression as, this is the multivariate expression for the residual sum of squares that we saw last week. And if you remember, maybe I can actually write quickly with my mouse, which is not very professional. But this, if you remember from last week, this was this sum of I equals 1 to n of all of the errors squared. Okay, so in terms of what this notation means in terms of the two vertical bars, this is actually the Euclidean norm. So this is the norm. We call it the norm, just like the standard norm that we use in linear algebra is the Euclidean norm. But this essentially, if I was to write it out for some vector, I can't do bold font, so I'll do it in terms of this. This is equal to the square root of this sum. This is some really good mouse handwriting, some trackpad handwriting, I want to say. However, it is taking a long time. I squared all to the power a half because it's the square root. So this is what this notation means in linear algebra. It's the norm, so it's taking all of the different elements, squaring them, summing them up and square rooting them. And so in this case, this is why we are squaring here, is because it undoes the square root and we end up with the sum of the errors just being, in this case, the y minus xb, because y is equal to xb plus the errors, and we'll just move xb over to the other side. However, it's also worth noting that when we're considering vectors, this is equivalent to writing the transpose of the vector times by the vector. So this is where this expression has come from. If I close my note now so I don't do anything accidentally. So this is where this expression has come from. Essentially, we have written the equivalent of this sum of the squared errors in terms of matrices. And we've also used in terms of the squares of matrix norms. And then we noted that that expression is also equal to this. I should also say, sorry, that this was 2 to the half, which is why once it's squared, it no longer is squared over here. Okay. Anyway, I digress. This is where I note that this is slightly beyond the scope of the course. This is for understanding, intuition, and interest. This is not something that I would recommend you brute force memorize if you're not already comfortable with linear algebra. However, we can expand this expression to receive this expression, and you remember this is just a function in terms of beta, and so what we're looking to do is we're trying to minimize this sum of squares in terms of beta, and when we try and minimize something in terms of its parameter, we take the derivative with respect to that parameter. However, this is obviously a vector of p plus 1 values, and we could do the p plus 1 different derivatives. However, we can fall back on doing the matrix gradient, which involves computing the derivative with respect to the matrix beta. I've skipped a step here. You can Google this step if you'd like, or ask ChatGPT or Claude to break it down for you. But essentially, you end up with the normal equations. You can see here that, again, if I go to my new favorite tool in terms of this pen, this doesn't have anything in terms of beta. So this, with respect, differentiating with respect to 0 gives this a 0. So I should kind of maybe say, I go d by d0 db. This has a beta term, and this has 2 different beta terms. So this term becomes minus, the 2 goes away because, was it because it's here? I don't think this 2 doesn't go away, but this has a square in it. So essentially this has a 2 coming down, and then the 2's cancel. This beta will go away. So this just becomes minus 2, and this will go away. So this is where on the left-hand side, we get minus 2x, the transpose of x times y. And on this side, we get 2 times by beta x transpose x. And then by setting all of that to 0, we get the OLS estimator, which is why we use the hat notation up here. I may remove that circle I just did, just so it's not unclear when people are looking at the notes, but that is essentially the step that we've done. We've differentiated this entire this function in terms of beta. We differentiated it with respect to beta. We set that entire expression to 0, and we rearranged to obtain the normal equations. And then, provided that this x transpose x is invertible, which is where this requirement that x has a full column rank from an earlier slide comes in, we can then times both sides by the inverse of x transpose times x. That cancels on this side, so the x transpose x goes away, and it appears over here as the inverse. So we can't divide in linear algebra, we have to multiply by the inverse expression. So this is our unique solution for our estimators from ordinary least squares. And you can see, this is just, we have defined x, and we have, in terms of data, we would have x and we would have y. So this is just a closed form expression that we can compute quite easily. The only thing that would take computational time, either for us to manually compute it or to have a numerical computer, on using Python or something would be this inverse of this matrix. So as I mentioned, this derivation is definitely beyond the scope of the course, but we can really, we emphasize that we see that we have this closed form expression for our parameter estimates. So now there's nothing holding us back from computing this manually if we would like. We just need to have a data set. We can define the column vector y, we define our design matrix x, and then immediately by plugging into this expression, using a numerical solver to compute this inverse, we can compute our parameter estimates without relying on any packages in Python. Oh, I didn't realize you stayed on the slide. Well, maybe this isn't my new favorite tool. Give me 2 seconds. Oh, this isn't very professional. Sorry, everybody. See, that's why I've not used it before. Okay. So to quickly highlight the connection to simple linear regression, we note that when we set p equals 1 and the design matrix x as simply the column bonds and a single column for x, we can quickly write that this x transpose x is written as n because it's going to be a sum of 1 times 1s, which is an n-length sum of 1 times 1s, which becomes n. Similarly, you can see the same expression coming through. This is just a sum of the x's, each one of them times by 1, sum of the x's all times by 1, sum of the x's squared. Same with x transpose y. And then when we do this computation with x transpose x inverted and x transpose y, we get the familiar expressions that we found previously. So this would be our beta hat, but because in this case we would end up with our first element of this matrix being y bar minus beta hat 1 x bar, and then the second one given by x x y over s x x. So this is just a direct generalization of the simple linear regression. So in terms of application, you don't need to consider them separately. You would always consider multiple linear regression, and just sometimes you may find that simple linear regression is the best model. Okay. Speaking of things that are slightly beyond the scope of this course, but is worth mentioning, is the hat matrix. So to kind of carefully introduce what the hat matrix is, we note that the fitted values, so the fitted values are what our model predicts. So we plug in our estimated parameters beta hat, we plug in our x's in terms of our design matrix with the data, and that outputs some estimates for our response, y hat. And the point is that we can replace x bar with this full estimate that we just derived. So the x transpose x inverted, x transpose y, all times by x from the beginning. And this is just a very long and tedious computation involving lots of x's and a y. And so we define this long and tedious computation of x's as the hat matrix. We call it the hat matrix because we are putting a hat on y. By applying the hat matrix, we take our it is describing the change from our observed response to the fitted values. Okay. So this isn't something we will delve into in great detail. We'll mention some of the properties, but it is quite a complicated thing to study because it is central to understanding the geometry of OLS and the corresponding properties of the residuals. It's something we will definitely look at in a lot more detail in more advanced linear regression courses. That's obviously not the focus of this course. Just some quick properties are it's symmetric. So this follows from this specific combination of operations on x. You can show that the transpose of h is just equal to h, and you can just apply it to this train of things and see everything flip around. It's idempotent, which just means that predicting it, this is an important word. So applying this matrix twice is the same as applying it once. It makes no additional changes. It doesn't keep moving things along. Its rank is p plus 1. one of the things that we potentially can think about in terms of this course is what it tells us, and it tells us the leverages on the diagonal entries. So if we compute H, it can tell us the leverages for those different points. So essentially a measure of how unusual the observation I's predictor values are. Remembering that if we have high leverage, that point has more influence on the fitted line. So it's a if we are able to compute H, it's an additional test to identify high leverage points, which potentially have very large influence on the fitted line. So just to kind of quickly describe what the hat matrix is in the most general way, without going into the details, it is essentially something called the orthogonal projection matrix onto the subspace spanned by the columns of X. So visually thinking about things, the data X is, each of the columns are essentially a dimension in this space, and the point of the matrix, this hat matrix, is it describes the fitted values of Y as the closest point in this column space of X to the observed Y. So it's essentially this linear mapping moving from Y to Y hat. So it's moving from Y in kind of moving Y into this column space of X, and it's directly linearly mapping to the closest point in that space. This is most certainly beyond the scope of this course. I only included it because I find this kind of geometric thought about there's this geometric understanding of statistics as essentially distances in abstract spaces as a really, really fundamental part to a deep understanding of statistics. And it's also one of the things that I found the most interesting and motivated me to study this topic and probability theory more in general. Was thinking about them as these kind of distances and spaces. So potentially it's a source of interest for someone out there as well. Maybe not though. Maybe you're not even listening to this lecture and just ignoring it. I really hope not. Another result that we can make use of is this hat matrix. Matrix. Sorry. And the residuals. So since the residuals can be written as the difference between our observations and our fitted values, we can write this as Y minus HY, and then we can essentially factorize using, where again, I is describing this n by n identity matrix. I got a little bit lazy with my subscripts here. And therefore we can compute the variance of the residuals quite easily because we know that H doesn't have any variance, but it does, or at least all of the variances are to do with X. And so everything's going to have this common factor of sigma squared, but this term is no longer the identity matrix. And so we conclude that the residuals are not independently identically distributed, even when the errors are. This is the last bit of code I'll probably go through in detail, but this is essentially repeating our computation of the OLS that I performed with simple linear regression with multiple linear regression. So using our design matrix, our response that we defined earlier, we specify here in NP linalg solve. This is solving this system. So let me quickly scroll back to really emphasize what this is doing. This is solving this system. So the way that NP-linalg solve works is it is computing, sorry, let me go back to it. It is computing a system like this. AX plus, oh, sorry, undo. It's assuming you're plugging in a system like this. AX equals Y, where X and Y are some matrices and A is what you're solving for. And so we by taking our inputs as the transpose of the design matrix multiplied by X, so this is XTX and this is XTY, we're getting XTX beta equals x, t, y. And this is what it's solving for. It's solving for this beta, right? And so hopefully that makes it clear, because you can see that if we scroll back to the page we just saw, that's exactly what this expression is that we're interested in. Xtx beta hat equals xty, solving for beta hat. So this bit of code is just doing all of the work for us. So this is doing all of our estimation of the parameters. We then, in this line of code, just compare them to our true parameters, just doing a quick computation and printing the output. Thank you, Claude, for formatting it nicely for me. And then again, thank you, Claude, for producing me this nice plot where I just highlight the difference between our estimates in the synthetic example and the true values. So that's what this final plot is. Let me just get my rubber out whilst I give you a chance to quickly look at it. You can see that we have our table above describing our true parameters and our estimated values. So you can kind of have a sense of how good this estimation was, but I think n equals 150. And then this visualization showing how close they were. Okay. So this section, I'm going to start moving a little bit quickly. I wanted to be more detailed at the start, but I'll maybe just quickly cover these as a highlighting as to, you know, it's not quite supplementary, but just recovering some of these reminders of why this is a strong estimator. It's unbiased, and you can show that by doing this computation where we factorize out this beta. And so when we take the expected value of beta hat, everything here has expectations, or this term specifically has expectation 0. So this all goes to 0. And this term is all that's left. And so we get this expectation of our parameter is the parameter, which just means that on average across many data sets, ordinary least squares returns the true parameter vector, which is a very desirable quality. Another property we want to cover is this the variance covariance matrix of beta hat. So essentially, what's the variance of this matrix? Because obviously, when we compute the variance, we're going to get a matrix of variances and covariances. First off, we introduce this term of collinearity, or we remind ourselves that collinearity refers to the case in which two or more predictors are correlated, so have some kind of linear relationship. When predictors are highly correlated, the reason why we're interested in this is because this matrix becomes close to singular, and that causes an OLS estimate to become unstable and start having large variance. This is something we'll look at more closely when we consider different models, because you will quite often see this problem arising in machine learning models, which involve linear algebra, is when computations result in some kind of singular or very close to singular matrix breaking down things and exploding the variance. So the covariance of beta, to compute it, we wish to compute the covariance of this term. Or essentially think about it as computing the variance, but it's multivariate, so it has to be the covariance. The diagonals will be the variances. So we note that we can write our estimate as this cy, where we've just defined everything before the y as c, because none of them have any variance, right? X is given, there's no variance there. The only variance is coming from y, because y has the noise component. So applying this linear transformation rule for the variance of matrices, again, I've left people to look at the proof of this, but essentially we have the variance of beta hat is equal to c times the variance of y times the transpose of c is the result. And the variance of y is sigma squared I. And so this is where this expression comes in. And then just a bit of manipulation, the variance of sigma squared I, this is going to be sigma squared across all of the different diagonals. And so we can write in terms of CCT, and then this simplifies to sigma squared times xt to the x to the -1. This is just plugging in, essentially this variance of sigma squared is collapsing away because it's going to be applied like a unit vector to these matrices. So we don't need to consider it as a matrix anymore. It can just become this scalar term. And then when we have CCT, we just plug in these terms into these two and cancel everything away. And you'll find that it boils down to xtx to the -1. So just some quick properties. The diagonal entries obviously give the variances of each of these parameters. So this is very helpful for the sampling distribution. Off-diagonal entries give these covariances between the different coefficients. So you can use this matrix to understand the relationship between the different parameters and how they vary with each other. Often we obviously need to estimate sigma squared, so we can substitute in this sigma hat squared, which we've looked at deriving in previous lectures using the residual sum of squares for, I always think it's RST, RSE, and RSS. This time dividing by the n minus p minus 1, so the order, what do you call it? Yeah, order power. There's a term there I'm forgetting. Sorry, it is technically 3 a.m., so my brain's a smidge fried. Anyway, I'll remember the term at the end of the lecture and be embarrassed, but it's okay. Essentially, the term that decreases the more estimates that you used in the derivation. So in this time, we're using p minus 1 estimators that we've computed, or sorry, p plus 1, and so we need to minus p plus 1. So if you think about this, we're doing n minus the number of parameters that we've estimated, and we've estimated p plus 1, so we do p minus 1. And therefore, the standard errors is just given as this square root, right? So we've got our estimate here, and we're just square rooting this term. Some precision drivers to think about is that if we increase the number of observations, this n goes up, the variance decreases because we've got more information that's coming from this term here, this n being on the denominator here. So this is, as n increases, this is shrinking. If you decrease the noise, obviously that we don't need to have this substitution, but if this is going down, so is the variance. More spread in the predictors means smaller. The effect on the variance is smaller because we have better leverage. This is decreasing. However, we have high multicollinearity. This term explodes, and so we have this multicollinearity is something that we'll talk about in future lectures because I'm certainly going to run out of time now. So this is just discussing degrees of freedom. There it is. That was the term I was forgetting with my sleep-addled brain. Not order. That's okay. This is just discussing what I was just mentioning in terms of why this is the unbiased estimator of sigma hat squared, why this is the parameter cost and the degrees of freedom. So I'll skip over the slide for time. I'll also skip over this slide. Please go through this if you'd like to see, but this is essentially just computing the sampling distribution. So it's performing this regression multiple times with different samples and plotting the parameters. So doing the same thing we did for simple linear regression, but this time with the 3 different parameters. You can see that they're centered around the true value, as you'd expect. So the true mean is 2.0, 1.99, minus 1.49. So this is just a visualization to show the unbiasedness of the OLS parameter estimates for multiple linear regression coming through when we kind of perform this Monte Carlo simulation, repeat multiple times, and also seeing the distributions coming through for each one. So I'm going to finish today, and I think I may have just enough time to quickly cover the last few slides at the end where I talk set up model selection, which we'll talk about more when we look at the Python code. Statistical inference in multiple linear regression. So the first test we look at, let me just get all the slides up, all the points up, and I'll move my floating head again. Oh, I don't want to make it bigger. I want to make it even smaller. Great. So t-tests for individual coefficients. So this, what we've just shown, going through this process of finding estimates for the variance, the standard error, and the location is essentially so that we can define the translation that we need to move in order to get to the t-test, the t-distribution test, right? So under the normal test, we could just assume that these parameters have some kind of, or under the assumption of normality, we can assume that these distributions are normal and can put them to z-tests, but we're assuming more generally that if we don't have enough, if n isn't large enough, we can just generally use the t-test, and that has um, that only has this centralized standardized form, and so we need to transform it. The uh, the corresponding t-distribution is determined by the degrees of freedom, which we've just defined, and the test statistic is this estimate for the parameter over the standard error of the parameter, and this is what we use to compare against distribution. And what you're testing here is you're testing whether or not there's evidence that the parameter, the null hypothesis, you're assuming the null hypothesis that the parameter is zero against the alternate hypothesis that it isn't zero, given all the other parameters are already in the model. So this is just, if you already have all the other predictors in the model, is there any remaining relationship between the parameter that you're adding and the response variable, or is it already completely described? So kind of equivalently, does this add any explanatory power beyond what the other predictors already provide? So obviously you can to make your conclusions about this, you can do your testing, your p-values. You would accept your alternate hypothesis, reject the null hypothesis for small p-values. But it's worth noting it doesn't mean that just if you have a large p-value, accept this null hypothesis, it doesn't mean that xj is unrelated to y. It may just be simply collinear with others. It might just have a very, very high collinearity with other parameters, and therefore they describe the response variable in the same way, and essentially one describes everything that the other could, and so the other gets ignored. In this statistics inference test, when I'm talking through all these different ways of performing statistical inference with multiple linear regression, a lot of them will feature very heavily when we discuss model selection. So I do recommend being quite familiar with them. This is already one example where you're essentially able to consider a model with this parameter against a model without this parameter is what this is testing. It's testing whether or not it's your parameter estimate is adding any significant information. So I'll skip through the Python code because we'll be covering this in more detail. And this is just the numerical computations in any case, but you can see how the estimate is computed, the standard error, the statistic, and the p-value. And you can go through these computations because this is how the p-value is being computed using the t-distribution down here. So nothing exciting. Another useful test, particularly when we're looking at model comparison, or in this case, just model testing in general, is testing whether any predictor is useful. So testing the null hypothesis that all of the parameters are zero against the alternate that at least one of them isn't zero. Okay, so it's testing whether any of the predictors are giving some information. For this test statistic, you can compute using the sum squared of the residuals and the sum squared of the errors. Sorry, this is for the regression. I always get that mixed up. The sum squares of the regression or the sum squares of the errors. This one divided by p because that's the order, the degrees of freedom in that case. We're not using any, or these cancel, I think, actually, and then this is from our degrees of freedom for the multiple linear regression. As I mentioned, this is essentially, you can think about the f-test as kind of this comparison of the explanatory power of with and without the parameter that you're considering. This test statistic follows an f distribution with a p n minus p minus 1 degrees of freedom under h naught. This is all something which I'm computing manually here, but this would be something that we read through our model output. So it's just important to understand what it's testing and how to read those outputs in general, particularly for your project. It's actually worth maybe noting here, I only have sort of 10 minutes to go, but it's worth noting that these manual computations are not a requirement for the project at all. This is to show you what the packages are doing. Please do use packages throughout your project. You will be, much more heavily assessed on understanding what they're doing and correct methodologies rather than being able to do these computations in Python if there's packages that exist that can do them. You should definitely make sure you know the what they are doing and the theory behind them, or at least be able to write them whilst you're reading about them online. Okay, I'm not sure I'll have time for all these slides, but I'll try my best. In the coming weeks, we'll start talking about lots of different models. Some of them will be for different use cases, but some of them will be for the same use case. So, for example, over the rest of this week and not so much next week, but potentially in future weeks, we're going to be discussing using multiple linear regression in Python. And we're also going to talk about some more complex versions of linear regression, so things like polynomial regression, things like generalized linear regression, which I will not cover in any great detail because that is becoming too hyper-focused on linear regression, but it's essentially manipulating and tweaking the underlying assumptions of the model, particularly about Gaussian distributions. And we need to be able to determine which model is best. And there are many different methods for doing that. There are brute force methods where you essentially try and consider every single model with every combination of parameters and features. That is far too time consuming computationally, and is very rarely considered, except maybe for the very simplest of cases. More likely, you're going to do some kind of stepwise selection. So forwards and backwards are different options. So forwards is where you sequentially add parameters. So you try and find the most significant parameter, start with that, and then find the next most significant, add that, and add again until you find some kind of balance between model complexity and number of parameters. Or you do backwards, where you start with the most complicated and you keep removing parameters until the cost of reduced accuracy is not matched by the improvement due to parsimony. And we'll talk about this trade-off. It's a very fundamental part of our model comparison feature. But this section, I'm going to sort of motivate that discussion by talking about some of the criteria that we use and also some of the problems. So model selection is this application of a principled method to determine the complexity of a model, aka which model is best. That can mean in the same model family. So, for example, like I just discussed, you could be choosing between multiple different regression versions with different, some have polynomial terms, some have cross relationship terms like x, beta 1x plus beta 2y plus beta 3xy, which is another version of regression that we can look at. But it also might be across modeling families. So it may have been logistic regression versus decision trees versus random forests, etc. So a strong motivation for performing model selection is to avoid overfitting. And so far, we haven't really spoken about overfitting because we haven't come across the point of overfitting is that you typically make a model too complicated and it describes the data too well till it gets to the point where it is describing and capturing the randomness as if it isn't random, and therefore it reduces its ability to make predictions with new data. So to be precise, overfitting is this phenomenon where the model is unnecessarily complex. We've added so much complexity that the model starts capturing the random noise in the observation and rather than the relationship. So the main drawback is this overfitting causes the model to lose predictive power. And the challenge of overfitting is that it's actually very difficult to quantify. There is no specific number that tells us when we have overfitted something. We typically have to perform multiple different tests and use multiple different criteria, and also use our judgment to tell when we are overfitted versus underfitting. So, for example, with this polynomial regression, which I know we haven't looked at yet, but this is adding higher and higher degrees i.e. different, more and more parameters to the model. And you can see that the line starts off looking relatively smooth, and as we add more and more parameters, it starts to become sharper and more jagged and copying the data more precisely. And we're having this, stagnation of the training RSS reducing, because eventually it essentially just lies perfectly on all of the points, and so we don't end up with any um, um, any errors left. We're reducing them down further and further. The um, first thing I wanted to talk about in terms of overfitting is this model performance term R squared. So I only have 10 minutes left, so I may speak slightly quickly, but I'll talk more about it when we put them specifically. We talked about R squared in simple linear regression as this measure of the how well the model describes the variance of the data. The problem is that R squared is not enough in multiple linear regression, because R squared always increases if we add extra parameters, extra predictors, which then have a corresponding parameter. So essentially, the more predictors we add, the better the model will be at describing the variance of the data, because it's got more to work with. Essentially, you're giving it more and more flexibility to describe the data more and more. And even though that sounds good on paper, the problem is that even if the predictor is pure noise and it's not describing any information for our response variable, it's still um, um, being treated. It's being treated with more and more power in R squared, and so R squared is always going up. This is a quick plot that I had. This was actually a happy moment for me, because I had ChatGPT quickly draw this code for me, because it was 2 a.m. and I really needed to get this lecture out, or recorded, I should say. And I had to do a correction. So I love moments when I can correct Claude, because it reminds me that I'm still needed in the world of data science, at least for the next month or so, until it gets even better. But anyway, you can just to quickly describe what this code is doing. It's essentially generating this observation data with standard normal, and specifying it's 25. And then we have to subset this generated data, so we don't generate new data every single time. We have to use the same data, essentially thinking about it as the same observations each time, but we're just adding more and more parameters. And you can see that R squared, even though it's not always going up by the same amount, it's always increasing. As we increase the number of predictors, the R squared is getting better and better. So if we just relied on R squared, it would tell us to keep adding parameters as long as we could, for as many as we can. But this is not ideal. And so instead we define this adjusted R squared. I'm just for the time being going to skip over this exact term and what it's meaning. I was going to go through it on my iPad, but I certainly don't have time for that anymore. I'll discuss this in a future lecture, but essentially we are introducing this penalty term whereby if we increase P, we are reducing, or sorry, here you can see if we increase P, we are shrinking this or increasing, because this is divided by, we're essentially having this term in terms of P where as we increase P, the penalty, and it reduces R squared. Sorry, the adjusted R squared. So the adjusted R squared, as we increase P, receives a penalty that's proportional to the size of P. So you can see if we produce, it compares the mean squared errors, not the row sums, and it can decrease when this added predictor does not reduce the SSE enough to offset the loss of degree of freedom. So the point is, if we're comparing models, we much prefer to use the adjusted R squared. If, say, for example, we're considering a 3-parameter MLR versus a 2-parameter MLR, we'll always use the adjusted R squared, because it gives this, it accounts for this, the increased parsimony of the model, and it penalizes complexity. The adjusted R squared only goes up if the penalty from the addition of complexity is less than the precision gain. this is something that'll be familiar to people using time series analysis too, in terms of adding different autoregress terms. Right, you never want to keep adding terms because you ruin your ability to forecast into the future. Okay, I'll finish off the lecture by quickly mentioning the two different information criteria we've spoken about before. Here are their derivations. So the Ekkane's information criterion and the Bayesian information criterion are essentially doing exactly the same job as the adjusted R squared. They compute this a value which summarizes the balance of the goodness of fit against model complexity. So you'll see throughout all of them this penalty term P coming in, where the point is that lower is better. So in this case, the P is increasing AIC, and so if this penalty from introducing more complexity is an offset by a reduction in the RSS of the model, then the AIC and the BIC will go up, and we will conclude that that model is worse performing. So the point is that AICs has a reasonably mild penalty term, but the BIC has a lot stronger one. So they have different use cases, but typically you produce them for all the models and you can compare them across the board. Okay. The last thing I'll quickly mention in the last 3 minutes, because I've been timing this lecture on my phone, is this partial F-test. So it allows you to compare nested models. This is actually more specific to the same modeling family. The AIC, the BIC, and the R squared can be used to compare across many different families. When we're considering families of regression, you can use this partial F-test, which compares a full model against a reduced nested model. I'm glad I left this to the end because I will go through this F statistic and how we compute these when we look at model comparison techniques in Python. Please don't get too bogged down with all of this algebra. But the point is that we use this partial F test when we're testing a group of predictors, i.e. all species of dummies or collectively, see if they collectively improve the fit. So we essentially have one model with multiple different parameters, and we take out a collection of them, and it's nested within that family of models, right? And so the point is that one individual t-test can't capture the joint distribution, and we perform this ANOVA test instead. We'll discuss this in lecture 12. So, apologies, I think I meant to delete this and move it to a later lecture, so I'll skim over that quickly. All right, so I'm really bang on time. This is a quick summary of what we've covered. This is just comparing the two side by side, and the similarities hopefully are more, hopefully now have been through the linear algebra, it's more clear that this is just a generalized multidimensional version of this, and the complexity of it only really comes from the linear algebra rather than any of the actual results. Also potentially the kind of more complicated tests we have to do for the inference, but I digress. We've, I think, successfully covered the multiple linear regression model. We've looked at the matrix formalization. We derived the OLS. We looked at some of the properties, although somewhat briefly, I admit. We looked at inference. We looked at the goodness of fit. We did not look at multicollinearity, and we will not be doing for a second. So next lecture, we're looking at fitting in Python. We'll look at how we handle categorical variables with dummy variables. We'll look at model comparison. We'll look at interaction terms, and we'll look at how we perform residual diagnostics with multiple parameters. So we're getting into the meat of linear regression, and hopefully we'll kind of be able to wrap that up on Thursday, and then the following week we'll start looking at classification methods, starting with logistic regression, because we can essentially take everything we've learned in linear regression and just apply the logit function to transform our nice straight line regress output to this binary classifier model. So that's the plan for the next lecture and for next week. But in the meantime, I hope labs have been going well. I hope your assignment is going well, um, which we do for the Sunday, and I will see you all on Thursday. Thank you. I'll stop the recording. Keep doing this.